Okay, this video is to go over the PowerPoint of nuclear stability, fusion, fission, and half-life. So this is just a step-by-step on how to determine the neutron to proton ratio. It's just a review. This was just some extra practice. Remember, small molecules like helium want to have a 1-to-1 ratio, while larger molecules, or I'm sorry, elements like lead have to have a 1.5 to 1 ratio in order for it to be stable. If it's stable, it's going to stay in place. If it's unstable, it's going to start losing little pieces of like neutrons, electrons, protons, all of that in order for it to be stable. So this is just some extra practice for you to figure out the neutron to proton ratio. So this is your mass number. So you have the name of your element here. So you should be able to figure it out by looking up at your periodic table. You determine the number of protons. That's going to be your denominator, protons. Or if you do the ratio, it'll be this number. And then you subtract your number of protons by your mass number, and that'll give you your neutrons. So for this, I just wanted you to do the ratios. You don't have to tell me if it's stable or unstable. Okay, so let's go over nuclear fission. So nuclear fission is going to be when heavy atoms, usually with a mass number greater than 60, are going to start breaking into smaller pieces. So fission, it's going to get smaller. It's going to get smaller. As it's getting smaller, the nucleus is going to become more stable because the force is going to be able to be stronger between the particles inside the nucleus. When you're making the nucleus smaller, this is called nuclear fission. Okay? This is going to release large amounts of energy because that energy that was holding the molecules together, it's going to disappear. It's going to start going into the environment, so it's going to release a lot of energy. There's a video for you to watch if you need some extra assistance with it. But nuclear fission is basically how nuclear power plants work. So they use fission in order to produce heat for their nuclear reactants and their reactors. This is going to provide like electricity. So areas that have nuclear power plants, they typically rely on these power plants to be able to power the city. However, if you've ever seen any movie or have seen any instance on the news where a power plant has exploded, it's going to wreak a lot of havoc because there's a lot of nuclear fission going on in this area. So imagine that all being released into the environment at once. It's going to literally destroy everything. There's another video for you. Now fusion. Fusion is going to be the opposite of fission. So instead of breaking up the nucleus, it's going to be adding to it. So it's going to basically combine small molecules in order to make a larger element. So like an example is hydrogen. Two hydrogens are going to come together and they're going to form a helium atom. Fusion reactions, they are going to release a lot of energy, but they need to happen in very high temperature environments. So this is very common in the sun, just because that's just that fuels life on Earth. So it absolutely can do this. Very difficult to do, like you won't be able to do that in like your normal oven, but in labs it can be recreated. But again, it is dangerous because of all the high temperatures that they are using. Okay, today we're really talking about half-life, and half-life is basically the time it takes for half of the nucleus to decay. Okay, so half of the nucleus to decay. So if our nucleus had, let's say, 100, one half-life would literally turn it to 50. So it's literally one half, or how long it takes for one half of the nucleus to go away. So each element is going to have its own half-life. So carbon is going to be its own thing. Nitrogen is going to have its own half-life as well. Like each one of them is going to have its own unique time. As it decays, so say you have like 14 and it decays to 7, this is a brand new element because what you have is different. So the amount of protons and neutrons you have in this one is going to be completely different than that. And remember, each element is identified by its own atomic number. So you just want to make sure you pay attention to that. The half-life of each element is constant. So if it takes 10 minutes for one half-life to occur, even if you have half of the molecule there, it's still going to take 10 minutes for it to happen again. So there's practice on the other one that we'll look at. So here we have a blue grid. It represents a quantity of C14, carbon 14. Every time you click one half-life, it's gonna go by and it's gonna turn red. So right now we have, this is all carbon 14, okay? We're starting, the no half-life has happened. We have 100% carbon, no nitrogen, and there's no ratio because there's no nitrogen yet. So as this is at, we're starting now, no half-life has happened. One half-life has gone by, and it went from being all carbon to now one half of it is carbon, one half of it is nitrogen. Okay? So our ratios are 50 to 50 because it has 50% of each, and this is our ratio. Then we're going to do another half-life. So it went from being 1/2 to now this is 1/4, and this is 3/4. Okay? Because we divided 50 by 2, and that gave us 25. You do it again. Now you're left with 12.5% when you were at 25 before, and here you got 87.5. Okay? So that's how it works. Each time you're just going to keep reducing by half. So if we were to do this again, you would only be left with one blue cube. You can do it with grams, it's the exact same thing. You just keep dividing by 2, and that'll give you this next number. You'll get a chart like this for some problems, and you'll be able to, you should be able to read it. So on this side, it's going to always tell you the percent that's remaining. And then down at the bottom, it's usually either going to tell you time or the number of half-lives that have happened. So here before we even start, we're at 100%. And then by one half-life, we are at 50%. And then by 2, you're at 25%. So when you get to 3 half-lives, you should be at 12.5%, and then 4 is going to be 6.625. So it's just going to keep getting smaller and smaller by half. You can also use this formula. So if they give you a word problem, you're going to put the amount that they'll tell you is remaining here. It's going to equal what you start with, and then this is going to be half because of half-life. And then the number of times, the n is going to equal the number of times of the number of half-lives that have happened right here. Okay, the number of half-lives that are happening. I'm going to show you how to do them with both. This one is going to work, but I think there's an easier way to do it. Okay, so stick tuned for the next video on going over the